Hello everyone. Today we're going to be doing lecture 13, rates of change, and this is going to give us a few applications of the derivative. So the first thing I want us to recall is the average rate of change formula. So we have the average rate of change of f of x over some interval, and we'll say from x1 to x2. And the average rate of change was given by f of x2 minus f of x1 over x2 minus x1. So this is a good old slope formula. This is the slope of the secant line through the 2 points. And I also want us to recall the instantaneous rate of change at x equals a is given by f prime of a equals the limit as x goes to a of f of x minus f of a over x minus a. So this was our second definition. We had two different versions of finding the derivative at a point, and this was definition number 2. So the difference between these two is that this is the slope between 2 points, and this is the slope of the tangent line at just one specific point. So we will see applications using the rate of change now. So we will use this formula here to apply this to other areas. So the very first thing, which you've already seen before, is with regards to velocity. So let's look at that. So we're going to suppose that s of t is the position function of some particle, something that's moving in space. Then we know from our previous lecture that the velocity of t is equal to the first derivative of the position. And I'll say this is the velocity of the particle. So maybe erase my period here. So this will be our first application. And let's go ahead and work through an example of this. So we're going to consider s of t equal to t cubed minus 2t squared plus 5. And I'm only going to consider this for positive t values because I'm going to think of this as time. But you could also have examples where I guess t is not restricted to be just 0 or positive numbers. But for this one, I'm just going to do t is 0 or greater. So here's our first part to this. We're going to find the velocity function. So our definition says over here that I just need to take the first derivative of this. So velocity is equal to the first derivative of position. My variable is t this time, but I can use all my rules that I've learned so far. So I'll use my power rule. I'll get 3t squared minus, I'll bring my 2 down, times 2 is 4t. Derivative of a constant is just 0. So this is my velocity function, as long as t is greater than or equal to 0. My next question is, when is the object or the particle, so particle, at rest? So this means that it's not moving. What would be helpful for this is the velocity, because the velocity is like, it's your speed and your direction. So if the velocity is 0, we're at rest. So let me put in parentheses that v of t should be 0 when it's asking you a question like this. So what I'm going to do is I'm going to take my velocity function, which is 3t squared minus 4t, I'll set it equal to 0 to find the specific times where the object's not moving. And if I do a little bit of factoring here, this is t3t minus 4. And this will give me two solutions. So t could be 0, and t could be 4 over 3, if you set each one of these equal to 0. So on a number line, I'll draw a small one here. I have 0, and I have 4/3. So these are the two times when the object is at rest. Now remember, for this application, I'm not really considering time over here, so this interval we'll kind of just ignore. We're really going to be concerned with this interval here between 0 seconds, if the time is measured in seconds, 0 seconds to 4/3 seconds, and then this other interval from 4/3 seconds to infinity. So we're really going to be focusing on these two as we move forward. I just want to let you know that. So now, for part C, I'd like to know when does the particle move in the positive direction. So for us in particle motion, we're going to say the positive direction is the right on the number line. So this will be the positive direction, and that'll be the negative direction. So we want to know when this is moving to the right. How are we going to do that? Well, not only does velocity have in it how fast something is going, but it also tells you in what direction it's going. So when velocity is a positive value, that means you're moving to the right. And when velocity is a negative value, that means you're moving to the left, which is the negative direction for us. And we've already talked about when it's 0. When it's 0, it's not moving at all. OK, so if I want to know when we're moving in the positive direction, I need to set my velocity function, which I factored earlier as this. I need this to be greater than 0. Well, this just involves an interval test here. So I have 0, I have 4/3. Remember, I'm not really considering that. I don't want to consider that. But for this right here, if I plug in an example, say like 1. 1 is a number between 0 and 4/3. If you plug that in here, is this true? Well, I get 1 times -1. So that doesn't work. You actually get a negative number here. So maybe instead of just aggressively writing an x here, what I'll do is I'll just indicate that this was a negative. This x is going to stay here because I'm not considering time before 0. If I plug in a test number here, say like 2, I get 2 times 2. So this one actually works. This is positive. So the question asks, when does the particle move in the positive direction? The answer to this is it starts at 4/3 and onward. So that whole interval from here on, the particle is moving in the right direction, the positive direction. And then if I went ahead and asked, when does the particle move in the negative direction, I have all the work basically done for me. I just grabbed the interval that wasn't the positive one. So this is my negative interval. So the answer would be from 0 to 4/3. Those are the times when the particle is moving in the negative direction. OK, so from here, I'd like to know how much distance does the particle travel in 2 seconds? So how much distance means when you start at 0, you begin moving. And I want to know, if you were to stretch all that distance out, how far did you actually move? So to do that, what I need to do is I need to first look at the spot where it was going left. It was going in the negative direction. So if you take a look at what happened, I'm actually going to draw it right here, just to give myself a little more space. So I'm over here. My points of interest are 0 and 4/3. Over here, we said that it was moving in the negative direction. So from 0 to 4/3, it's moving to the left. And then after that, it's moving to the right. So to get my total distance, I need to take all the distance it traveled to the left. Right here, what did it do? It actually turned around. So it's going back the direction it came. So it's going to start kind of counteracting where it went. So I can't just consider the whole interval from 0 to 2. I need to break this up. So first I'll get the total distance from 0 to 4/3. Then it turned around and went the other way. Then I'll take that distance from 4/3 to 2. So let's set this up. I'll show you how this works. So I'm going to write the total distance. The total distance for 2 seconds is equal to the distance from t equals 0 to t equals 4/3 plus the distance from t equals 4/3 to t equals 2. I have to separate it at this turning point because it goes back on itself. It's basically overlapping where it went. So I need to separate these two. And then from here, to get the total distance, I'm going to take the absolute value, just because I don't want to mess with the actual, the sign. I just want to know how far the object traveled. So I'm going to just take the absolute value of whatever difference I get. And this is the difference in the position. So this is where it is at 4/3 minus where it is at 0 plus where it is at 2 minus where it is at 4/3. So again, I want distance traveled. That's not a negative thing. So no matter what position it's in, I just want to take the positive of the difference. So what this involves is you're going to plug in 4/3 into the position function up here. You'll plug in this 0, and you'll plug in this 2, and you'll calculate this out. So what this is going to give you is, for this first piece, I'm going to get 64 over 27 minus 32 over 9. And then for the second piece here, I'm going to get negative 64 over 27 plus 32 over 9. And it turns out that this is equal to 32 over 27, which is equal to 64 over 27 units. OK, so that was one application of using the derivative, is to find things like the speed and velocity of an object, or to find how far something has traveled. But now we're going to look into marginal cost. So let's let c of x be defined as a cost function of producing, a cost function for producing x number of units. So a company wants to produce 50 objects. They would plug 50 into this function. It tells you how much it costs the company to actually produce 50 units. So marginal cost is equal to c prime of x, which is the instantaneous rate of change of c of x, of the cost. So what this does is, the marginal cost, it approximates the cost of producing an additional unit when we have produced x units already. So it lets you know, it's an indicator of how much would it cost to produce just the next unit of a good. So let's look at an example of this. So let's say that the cost function for a company, they're making some kind of object, and it's c of x equals negative 10x plus 0.5x squared plus 100. So for example, the cost to them to produce 0 goods would be, if you plug in 0, it would be 100. So you might interpret that to be something like, if they just let their factory sit and didn't produce something, it would cost 100 to pay the rent or something like that. So if they produce nothing, it would cost 100. OK, so first what we're going to do is we're going to find the marginal cost of producing 50 goods. So let's try that. So first, to get the marginal cost, you're going to take the derivative of the cost function. So that's this. You'll take the derivative of negative 10x and get negative 10. Because that is just the power rule. You just bring one down, lower the power. Bring this 2 down here. 2 times 0.5 is 1. So I get 1x. Derivative of a constant is just 0. So this is the marginal cost function. And then if I plug in 50, like the question is asking me to do here, I get negative 10 plus 50 is 40. So this means it will cost approximately, that's what my wiggle lines here will mean, approximately $40 to produce an additional unit when x equals 50. So to get to my 51st unit from already having 50, it would cost me $40 more. That's an approximation for that. We have this approximation. However, we can go ahead and just find what that is. So let's find the actual additional cost. We can do this because we have the actual formula. So the actual additional cost would be c of 51, producing the next good, minus c of 50. OK, well, what's that equal to? You're just going to plug these numbers into this equation right here. So I'll get negative 10 times 51 plus 0.5 51 squared plus 100 minus, I'll go down here because I need some room, plug in 50 into the cost function. So negative 10 times 50 plus 0.5 50 squared, and then plus 100. Some ways to make this calculation a little easier is you might see that there's a negative sign being distributed here. So this negative 100 will cancel with this 100. So that's one thing to see here. Another thing to see is that if I have negative 10 times 51, and I have negative 10 times 51, and here I have positive 10 and 50, you could think about kind of grouping those together. And then I have these other two terms here, this 0.5, here's 51 squared. And I have another one here, minus this 50 squared here. So I have 0.5 in front of both of them, so I can factor it out. And I have this 51 squared minus this 50 squared. So if you go ahead and go through all this calculation here, you're going to get that this is equal to $40.5. So this is the actual change in cost. So to produce, if you had 50 units and you produce that additional unit to get your 51st, it actually cost you $40.50 to do that. This marginal cost function approximated what the next one would be using 50 here. And it approximated it to be about 40. So it was only 50 cents off, so it's a pretty good approximation. All right. The next thing I'm going to talk about, it's not exactly like velocity or money or like an actual like application, but I'm going to go back to graphs. We talked about using the derivative to find the slope and then interpreting the actual graph and the slope graph. So I'm just going to talk a little bit more about that for higher derivatives. So I guess the application I'm talking about here is higher derivatives. Basically taking the derivative of a derivative. That's what this is. So f prime of x is the slope at any x value of f of x. However, f double prime of x, f triple prime of x, ... can also have useful interpretations too. It's one thing to remind you that, yeah, you can take derivatives of derivatives and you keep taking derivatives, but also higher order derivatives do come up in application as well. So for instance, remember that the acceleration of a particle was the second derivative of position. So if you take two derivatives of position, you get to acceleration. So that's one example of how a higher order derivative actually has application. Let's go ahead and try to find a higher derivative of f of x equals x squared e to the x. We're going to get lots of good practice with the product rule by doing this. So my first derivative, I'll do that right here. We're going to use the product rule. The derivative of the first one is 2x. We're going to leave the second one alone. And then plus, switch the order. Leave the first one alone, which is x squared. The derivative of e to the x is e to the x. We learned that in a previous video. So this is my first derivative. I could take a derivative of this one. So I'll come over here and start taking the second derivative. Notice it's going to involve some more stuff, right? Let's go ahead and rewrite this. It's always nice to rewrite something and make it look nicer before taking the derivative. I've mentioned that. Both of these have an x in common. Both of them have an e to the x in common. So if I factor this, the first derivative, I'm left with 2 for the first term here, after I bring out these two, plus I've factored out an x and e to the x, so I have an x left here. I'm going to take the derivative of this. So here's a function, and here's a function. However, one of my functions is a product. OK, let's do the derivative. So what is the derivative of the first one? Well, it's x e to the x, so that's a product rule. So the derivative of this first one is 1 e to the x plus x e to the x. So I took the derivative of this by doing a product rule. Leave the second one alone, 2 plus x, plus, and then leave the first one alone. That's good, because we do just want to rewrite that. That's a lot of work. And then what's the derivative of the second one? Well, that's just 1. Because the derivative of a constant is 0, and derivative of this is just 1. So this is the second derivative. And we could keep doing this on and on and on. So that's some practice with higher order derivatives. Last thing I kind of want to show you, I'll put it down here because I have a bit of space. And so let's look at this. Let's look at a much simpler example. Let's say f of x is x squared. Let's say f prime of x, what is the derivative of this? It's just 2x. And then last, what's my derivative of 2x? It's just 2. Let's look at the graphs, because these are easy to draw. X squared is just a parabola, just like this. The line 2x starts in the middle here at 0, 0, and it has a slope of 2. So it looks something like this. I don't need to be that careful. It looks something like that. Finally, what is the equation of the line y equals 2? Well, that's just a horizontal line at 2. And I want to revisit that idea of comparing an original graph to its derivative. Look at this. On this side of the graph, we are decreasing. The slopes are positive. So on the derivative graph for this one, we're negative. And the derivative right here is 0 because we're changing direction here. So the slope here is 0, and the slope here is 0. And then here on the graph, we're increasing. The slope is becoming much greater and positive as we go more and more this way. And that's why this is it's reflected here as being positive, and it's growing. What's the slope of the first derivative graph? It's 2, right? Everywhere on the graph, it's increasing. Unlike this one, where it has a decreasing bit and an increasing bit, this one's increasing. The slope is 2 everywhere. So that means the derivative of this graph is 2 everywhere, because there's only one slope this time. It's 2. And then if I were to do a third derivative, this would be 0. That's not very interesting, right? So hopefully you see the connection between these, right? This is always 2 because the slope's always positive here. This one is positive on the right because this has a positive slope here, and it's negative on the left because this has a negative slope here. So I want you to see how those are all interconnected. It's very important that you see how a derivative and the graph it came from relate to each other, both visually and algebraically. All right, I think that's it for this video. Thank you so much for watching. Do all your homework as usual, please, and reach out to me if you have any questions. I'll see you in the next one. Bye.